So if you want to do 15, find 50% of 3/4. So find, that's going to be your x. So x is 50%. You can write that as a decimal times a fraction. In this case, you probably don't want to multiply a decimal and a fraction, right? So you've got to change one of them. Two ways you can do this. I personally would just change this to a fraction. Remember, a percentage is a decimal or a fraction. So x is 50%, that's 1/2. If I did 50 over 100, times 3/4. And that's going to give you 3/8, right? If you did it with decimals, then you could have changed this guy to a decimal. So you could say x equals 0.50 times 0.75.
Kelly Thomas.
Right. So. Either way. But typically, if you get a fraction, the answer is going to be in a fraction form. So, percent change and then error, percent error. So the first paragraph here just talks about relationships to the original, basically, is what we're looking at here. If a price of a product increased or decreased by $10, would that be a significant change? Well, it depends on how much the product was. And they give the example, a $1,000 computer increases $10. People aren't going to notice that much. But if your $5 notebook increased $10, went from $5 to $15, you would think that was crazy increase. But it was the same dollar amount. They both increased $10. Why did it seem different for the computer versus the notebook? Well, the original price was different. And so paying $10 extra on a $1,000 computer doesn't seem as big as paying $10 on something that's $5. Think about shipping charges. If you're buying a computer and the shipping charges are $10, that doesn't seem like a big deal. If you're buying a $5 notebook and the shipping charges are $10, you're paying more for the shipping charges than you are for the notebook, right? And so it seems like a big deal. This is why, because it's all relative to what it originally cost. This is what we look at when we look at percent change. So they actually give you the definition there of percent change. You look at the amount of change divided by the original amount. And then you multiply that by 100 to get it in percentage form. So if you divide the amount of change by the original, you're going to get a decimal. And then if you multiply by the 100, you're going to get the percentage. So percent change is the amount of change divided by the original amount multiplied by 100. All right? Original amount. That will make a difference. So let's look at the example. Example 1, middle of page 117. A baker decides to raise the price of a loaf of his specialty bread from $3 to $4. The new price resulted in a large drop in sales, so he reduced it back to $3. Determine both the percent increase and the percent decrease in the price of bread during these changes. All right? So the first thing they want here is the percent increase. Percent increase. This means it went from a lower amount to a higher amount, right? So remember, our formula is the amount of change. Well, it went from $3 to $4. How much did it change? $1. How do we know that? Well, we subtracted 4 minus 3. All right? We divide that by the original amount. Well, if it went from $3 to $4, what was the original amount? 3. So we have 1 divided by 3, and we multiply that by 100. It's approximately 33%. 33% increase. When you're talking about increase and decrease, you don't do positives and negatives, all right? You actually tell me, is it an increase or a decrease? It's pretty easy. If it goes up, it's an increase. If it goes down, it's a decrease, right? But then they want the percent decrease. Some people would automatically think it's going to be 33% decrease. However, it's not. If we look at the percent decrease, the difference in price is still $1, right? But this time it went from $4 to $3. So the decrease amount is still $1. But here, what's the original? It's 4. And when we do 1/4 times 100, we're going to get exactly 25% decrease. So you can see how the same amount of increase or decrease can be different if your original amount you're basing it off is different, right? So when he increased it, he was basing that off of the $3, but when he decreased it, it's basing it off of the $4. You always base it off of the original amount of the change. All right? Always base it off the original. You don't have to worry about positives and negatives. Just subtract the smaller number from the larger. But the denominator is always going to be the original amount. Always going to be the original amount. Let's look at the next example. Last year, 1,056 people voted in the city election. This year, only 912 voted. Find the percent decrease to the nearest tenth of a percent in votes cast. All right? So, I need to see what the difference is, right? The percent decrease is what I'm looking for. How do I find the change? How do I find the change? What do I do to find the number of votes it changed? My numerator here, this what I am going to put in the numerator, right, is the 1,056 minus the 912. And yes, my denominator is going to be, like he said, my original amount, which was the 1,056, right? When I subtract those, I get 144 divided by 1,056. And I am going to multiply that by 100. This one they want to the nearest 10th percent, all right? The nearest 10th percent. So that means we don't just want to leave it at the whole percent. We want to take it out to a decimal place. And you actually need to look 2 decimal places to be able to round that correctly, right? So if I'm rounding to 1/10 of a percent, I need to look at the second decimal place to round it correctly. But this decreased by 13.6%. 13.6% decrease. All right. So they've given us this word problem about this city, and it tells us the city is expected to grow by 7% over the next 10 years. They also give us the current population. All right, so they've told us what it currently is, and they've told us the growth, all right? But they want how many people are planned. So I can easily figure out how much it's going to change, right? If I want to figure out how much it's going to change, I'm just going to multiply 35,000 by 7%, which is what? 0.07, right? And if I do that, I'm going to get, what, 2,450. Does that tell me how many people they plan on having? Well, no, because that's definitely not an increase if it went from 35,000 to 2,450. If I want to know how many people they're actually going to have, I need to take the original amount and I need to add the 2,450 to it, which gives me 37,450. All right. There's another way to do this. When they want to know what the new thing is going to be, you can actually take the original and you can multiply it by 1.07. Why does this work? When you multiply it by 1.07, by the way, you get straight into the 37,450. Think about distribution. 35,000 times the 1 plus the 0.07. I'm multiplying it by the original amount, 35,000 times 1. That gives me the 35,000. And I'm adding to it the growth of 7%. Distribution tells me I can go ahead and add those two and multiply, which is what I did here. So when they want the new amount, you can actually take your percentage growth and multiply it by 1 plus that. And that gives you the growth of it. Now decreasing is a little bit different, but with growth you can do it. So you can really do it either way when it's growing. You can find out how much it grows and just add it to the original, or you can just multiply by the 1 point, the growth amount. And it will give you the new amount as soon as you're done without the addition. So both ways work here. This one is decrease, all right? So decrease is a little bit different. With decrease, you don't usually do the 1 plus because obviously adding is not going to work. And so if you do 1 minus, you're going to find you have something less than 100, and it actually works. But in this case, we're going to do it a little differently because we want to make sure we're clear here. First of all, you'll notice that they say he was able to decrease his time. So this is a clue that you are going to be going down, which, by the way, that's a good way to logically check your answer at the end, okay? He decreased it by 13%. And they gave us his time as 2 hours and 47 minutes. Now, there are two ways to do it with time. Either you can convert it all to minutes, or you need to use decimals. But if you use decimals, it's not 2.47, because that 47 minutes is out of how many minutes in an hour? 60. So if you do decimals, a lot of times people get confused because they think, oh, 2 hours and 47 minutes is 2.47. It's not true. That would be if there were 100 minutes in an hour, right? But there aren't. So typically for this, is how they did it here, they just converted all to minutes. It's just easier. And so if I converted this all to minutes, what would I do? Well, I would just change these hours to minutes. How many minutes is 2 hours? 120. Plus the 47 minutes. So how many minutes altogether was his time? 167 minutes. All right. He decreased it by 13%. Well, in order to figure out how many minutes he decreased, I need to know what 13% of 167 is, right? So what do I need to do to that 167? I need to multiply by what? The 13%. How many minutes did he decrease? So what is 13%? We're going to do two ways. We're going to show this two ways. The first one is just figuring out how many minutes he decreased. 21.7. We'll just round. Or we can say 1 if y'all like. All right, 21.71 minutes. Is this what his new time was? No, that would be really quick, wouldn't it? All right. So if he decreased his time by 21.7 minutes, this was his original time, right? Then we would have to add it in there, right? So it was about 22 minutes. So about what? 197 minutes or whatever. All right. I have a question here, though. What's another way you could do this? So if it's 13%, what's another way to do this?
0.13.
So we added 1 to the other one when we were increasing. Subtract from 1. Subtract 1 from, right? So it's what? 87%, right? Does that make sense? There's two ways to do it. You can take this and subtract it like we did, or you can take this, so we can actually subtract that and figure out his time, right? Or we can take this and multiply by 1 minus this, right? Which is 167 times 87%, or 0.87. So when you're decreasing, you subtract from 1. When you're increasing, you add to 1, right? Or you can figure out what it did and subtract, and figure out what it did and add, right? So there's two ways to do it. Just like we did the 1 plus when it increased, or we just found out the increase and added. You can do 1 minus and multiply, or you can find what it decreased and subtract. Two ways to do it. 13% subtracted, or 87% straight, and it would give you the answer. All right, let's try some of these. All right, so this one is find the new amount It increased 700 by 40%. It decreased 600 by 55%. And they want the new amounts. All right? So for these, you can either find how it changed and add or subtract, or you can go straight to multiplying it by a different percentage. So percent error follows in line with percent changes, but now we're looking for a different type of answer, all right? And they give you the example here above this definition. The accuracy of an experiment is often judged by the percent error, and sometimes they'll give you stipulations. So like manufacturers will do this. They will say, we want to make this to a specification, and we will allow there to be this percent of error, meaning if I want to make a basketball to a certain specification, then they will say it can be this percent off and it's still okay within the realm of how we want to make it. They'll do quality control and they'll say, well, if I'm making maybe the wheel for a skateboard, I want it to be this diameter and the percent error can be this, because as long as it's with this percent error, it's not going to affect the safety or the functionality of what I'm trying to make. And so they'll give specifications of what that percent error can be. And so they're looking for, because if they're making maybe a wheel for a skateboard, clearly there's a point where it's going to make a difference if it's too far off from what they're trying to make, right? But if they have a percent error and they make sure they are within that percent error, then they're all good, right? So they always have these specifications when you make something. Experiments are one of them. So if you get into chemistry, you're going to have percent errors that you can be within and still be considered correct within the experiment. So the value that you are experimenting, or like if you're producing something, the value that was actually produced, minus the known value, that's the parameter that they have set, or what you expect, divided by your known value. So when you're talking about percent error, the experiment is what you actually get. You are going to subtract from that what you were planning to get, like the known, and you are always going to divide by the known. You'll notice in this one that we have absolute value. Absolute value is there because honestly, it's just like the percent change. I told you that it didn't matter as long as you subtract the smaller from the larger. It's because you're going to tell me, is it decreasing or increasing? Here, for percent error, they really, when they give it, they say it's really on either side. So they don't care if you are too large or too small, as long as they know that you're within certain values, okay? And so that's why they put the absolute value here. You can subtract and you don't have to worry about your positive, negative. You can just drop that positive, negative, or you can always subtract the smaller from the larger. What matters is that you always divide by that known value. All right, so let's look at this example. In chemistry class, Jonah determines the density of copper to be 8.83, while the accepted value for copper's density near room temperature is 8.96. Determine both his experimental error and his percent error. All right? So the experimental error is what your numerator is going to be, okay? And your percent error is what happens when you divide and multiply by the 100. So first of all, we want to know what his experimental error was. This is the numerator without the absolute value. All right, so experimental error is going to be his experimental value minus the known value. So what he got versus what he was expecting to get. In this case, he got 8.83. He expected, or the known value was 8.96, which means his experimental error was negative 13 grams per centimeters cubed. All right? This guy can be negative. This just tells us that he was below what he expected. So that negative here just tells us if you fall below or above what's expected. But when we talk about percentage, we're going to take that without the negative. We're going to use absolute value there. So his percent error here is just going to take this number, absolute value, so the 0.13 without that negative, divided by what was expected or what was known. Which value was the known value? Which value was the known? What are we going to divide by?
8.83.
That was the experimental. That was the known, 8.96. All right, so by known, they mean expected, or what you, for example, they said the known value of the density. The experimental is what he got when he did the experiment, right? So we're going to take that, and we do multiply that by 100 because we are doing percentage. And you will get rounded, so they did round it to 1 decimal place, approximately 1.5% off. So he was negative 0.13 grams per centimeters cubed off, and he was 1.5% off from what they expected him to get when he did his experiment. So experimental error is subtracting what you actually got when you did the experiment, or when you did the product, or whatever you're doing, manufacturing the wheel for the skateboard, your actual diameter there, minus what you expected to get, minus the known. That is your experimental error. That is the actual amount you were off. If they want your percent error, that's when you do absolute value divided by what was known or what was expected to get before you did the experiment. And then, of course, you multiply by 100 because you want to get percentage there. Next one, percent difference. For percent difference, we are strictly figuring out how far off it is from the distance, all right, from the average of the two. So we're going to take the first value and subtract the second value. You'll notice we still have these absolute value marks. And we are going to divide it by the average of the values. How do I find an average of two values? Average. How do I find an average? Right, there's two values, so you add them together and divide by 2. All right, so let's look at this example. We have Suzanne is asked to determine the volume of a cylinder. Using water displacement, she arrives at the answer 15.64. Then she measures the dimensions and calculates a volume of 14.01. Find the percent difference, okay? So percent error is what you got minus what you expected divided by what you expected. That is percent error. This is percent difference, all right? So for this one, we are just going to subtract these two numbers here. That's going to be my numerator, 15.64 minus 14.01. It will be positive. But now I need to divide by the average, all right? So my average then is going to be these two. If I'm just calculating the average over here, I'm going to add them up and divide by 2. All right, what is my average then? What is my average? All right, so this average is 14.825. All right, so if I subtract these two, what do I get if I subtract these two? 1.63 divided by 14.825, and I am going to multiply that by 100 once I get that answer. And you should get approximately, when you round, 11%. So in your calculators, you're going to divide these two and then multiply by 100. All right, so the key is that you know how to find an average. The average of two numbers is just add them and divide by 2. All right, so you need to know these terms. Percent error is going to be what you got minus what you expected divided by what you expected. Percent difference is the difference of the two things you got divided by their average. Okay, so make sure you know those terms and the difference in those terms. All right, I want you to try one. So there are two things that can happen with experiments. One can be like the first example. You have a known value. And so for the known value, you're like, I'm going to perform the experiment and I'm going to see how close I got to what I thought I was going to get. Sometimes then you are doing multiple tests. So like in this case, it says Suzanne is asked to determine the volume of a cylinder. Using water displacement, she arrives at an answer of 15.64 cubic centimeters. She measures the dimensions and calculates a volume of 14.01 centimeters. Find the percent difference of her results. So this is different than percent error. If they asked for percent error here, then we would assume the calculated one without the water displacement would be the known. And so they just want to know how far off you are. In this case, you are looking at the average between the two. So percent error is a stagnant. And by that I mean whatever is known, that is the value you're going to divide by. All right? But when you want percent difference, then you are going to do the same thing at the top. You're going to subtract and take the absolute value. But notice what you divide by here. We did not divide by some known or the original value, like when we're finding change in price or something. We divided by the average of the two. So what do I mean by average? How do I find an average of two numbers? So if I want the average of the values, I actually have to add them up and divide by 2 to know what my denominator is going to be. And this is called percent difference. Percent difference. So they want to know the difference in the percent that was versus compared to a known value, which is percent error. So for this one, I'm still going to subtract them. So we're still going to take my first value, which in this case was the displacement, 15.64, and we subtract the second value, which was when she calculated it, 14.01. That is going to be my numerator. But for my denominator, I need to know the average. And so I'm going to take the average. I'm going to take those two numbers, add them up, and divide by 2. I'm going to take the average here for my denominator. And when you do that, you get 14.825. Add them up, divide by 2. That is what I am going to use here for my denominator, 14.825. And then I am going to multiply that by 100. When you subtract these, by the way, you get 1.63. And it's positive, but absolute value is going to be positive there. And then you divide by the 14.825. Multiplied by 100, they rounded to 11%. 11% difference, okay? So this is like a precision. They want to see how precise you are. If you were to do the same experiment multiple times, this is really what you would want to do. Granted, measuring the cylinder, why is that not considered a known value? Because it could have been off when she was measuring. Her measuring tool might not have been precise enough, right? And so this is just seeing how precise you are to the two experiments that you did. One she did with water displacement, where she put it in and saw how much the water changed, the volume of the water. The other one she measured, but either way she's technically doing an experiment because she's using a measuring tool that might not be as precise as what some could be. And so this is more to see how precise you are in the two different experiments versus the copper, where we know what the density of the copper is. It's a known value. She did two different experiments here. And that's the difference between these two.